much. Hello, everyone. Hello, everyone, and thanks a lot for your kind introduction and for giving me the opportunity to present my recent work on methods for detection of magnetic field polarity with NB centers in a diamond. So in this first slide, I show right away what is the main results, the new results that I will present in this talk. As you can see, when you activated the
Fabrizio, please share the screen to
sorry,
start
it's not
the presentation.
Sorry, it's not shared yet.
I can see it.
You can see it, yeah. In fact, everyone can see it.
Yep. Yep.
Can you see it?
Yeah, look, it looks good on my end.
Okay, so can I continue then?
Yes, please continue. Thanks.
Okay, so as you can see in this image, these are the key results of my presentation, which show that by switching the polarity of a magnet, you can see that the ODMR spectrum is completely reversed. And this effect can be exploited for detection of magnetic field polarity and for applications, for instance, in digital information, as well as for understanding physical phenomena in condensed matter physics. So I assume that most of you are familiar with MV centers and ODMR methods. Therefore, I will go straight with introduction to MV centers based magnetometry. And I will delve with methods enabling detection of magnetic field polarity based on a biased magnetic field, circularly polarized microwaves. And then I will show you two new methods that I have implemented in my laboratory based on lock-in detection of a magnetic field based on amplitude modulation of a magnetic field with a conventional ODMR, and also off resonance without using a microwave. Therefore, this can also be called all optical. And then during the presentation, I will also give some example application of these methods in magnetic reading nets and nanomagnetism. And I'll conclude the presentation with a summary comparing the different methods with giving the pros and cons of each one. So magnetometry with the MV centers show particularly several advantages compared to traditional magnetometry techniques like squid, Hall sensors, MFM, muon spectroscopy, and because it essentially provides very high sensitivity down to picotesla, as well combined with the high spatial resolution to nanoscale, so 4 nanometer scale. And in addition, it provides a non-perturbative probe and high tolerance for working at very broad experimental conditions, like temperature from 1 Kelvin to above room temperature, pressure from ultra-high vacuum to larger than 60 gigapascal, and large magnetic fields as well. And allows, compared to other conventional methods, a complete vector field reconstruction, avoiding misalignment issues related to misalignment and drift. This is because MV centers in diamond can exist in 4 different crystallographic directions, which are fixed and insensitive to misalignment and drift. So when using MV center for application for magnetometry, then there are essentially 3 sensing platforms that have been developed so far. These are the bulk, the scanning tip, and the nanostructure or membrane. So the bulk can be realized by integrating a single diamond crystal with a few MV centers, which are shown here with the red spots, or with a very high concentration of MV centers. The low concentration MV centers provide high resolution, and but however provides low coverage of the sample under investigation. And in addition, provides also inconvenient optical access because the sample is placed on top of the diamond from the side where the optical access for excitation detection of the fluorescence from the MV centers takes place. Instead, the ensemble layer, where we have a high concentration of MV centers, provide high coverage and fast imaging because the large number of concentration and enhance the sensitivity, which scale as a square root of a number of spins, on the other hand, it provides a low resolution. And again, also this is affected by the problem with the inconvenient optical access. The second platform entails the scanning tip. The scanning tip is essentially is made by combining optical spectroscopy with MV center that is attached to in general, is a nanocrystal that is attached to the end of AFM tip, atomic force microscopy tip. And this provides high resolution because then we can scan the tip over magnetic sample and then we can have a very resolution to nanometer scale, and it provides also high collection efficiency because the sample here doesn't obstruct the fluorescence emission. But on the downside is that it provides a slow detection mode because we have only one or few MV centers in this case, and therefore this decreases significantly the sensitivity. And therefore every pixel, in order to have enough signal, you have to record several spectra and average them out. And final, that the last sensing platform is based on a nanostructure or membrane, where this nanostructure can be integrated with MV centers, and they have the advantage that it provides high collection efficiency, and there's no sample obstruction. But on the other hand, they provide low coverage, and they are difficult to fabricate and to handle. So each of these platforms has been tested against the sensitivity to DC, AC, electric, and magnetic field, as well as stress and the temperature. And typically for each platform, you can achieve, as far as magnetometry is concerned, you can achieve nanotesla per square root of Hertz sensitivity. And eventually you can also combine a different platform to, let's say, compensate for the disadvantages of one or the other. So when using this MV center to reconstruct the vector magnetic field from a sample, there are have been developed essentially two methods. One is called sequential addressing method, where essentially a bias field is applied to the sample to investigate, with this bias field has to be much lower than the coercive field of the sample. And then the bias field is applied along one of the crystallographic direction of the MV center. In this way, you single out a particular resonance line, and then by measuring the difference in the frequency between the resonance line, you can extract the magnetic field component along that isolated MV center direction. And then by repeating the measurements by aligning the bias field along the other three crystallographic direction of the MV center, you can calculate you can extract all the B1, B2, B3, and B4 components of the magnetic field of the sample along the four crystallographic direction of the MV centers. And then once we have these four components, you can mathematically calculate the magnetic field component of the sample along the X and Y direction of the laboratory frame. So this sequential addressing is the downside is that it provides a slow method, because every time we have to align the bias field along each orientation. And therefore, a different method has been developed to make it the acquisition faster, enable therefore faster reconstruction of the magnetic field vector. And this has been done in this publication by Schloss et al., where they have developed an algorithm that enable to fit the data of a single ODMR spectrum. And from the fitting of data, they can extract the magnetic field component along each crystallographic direction simultaneously. And by obtaining this information, they can use then a matrix transformation to obtain the magnetic field component along in the laboratory frame. And so this provides a 4 times faster method compared to the sequential addressing that I've shown previously. So, however, these methods have been used by using a sensing platform based on the bulk, on diamond. However, when we want to detect the magnetic field vector by using the scanning tip platform, then we come out with an issue where we can definitely still detect the modular direction of magnetic field, but we cannot extract the magnetic field polarity. And magnetic field polarity could be a very important property if you want to investigate, for instance, the magnetic bits of hard disk device, or if we want to investigate magnetic phenomena at nanoscale. And indeed, the ODMR spectra are completely inherently independent of magnetic field polarity, because from the difference of the location of the dips, we can only extract the magnetic field amplitude, magnitude, but not its direction. So one way, therefore, we have to combine ODMR with some other methods in order to extract the magnetic field polarity. The most used methods is the DC bias field. And also I will show some other methods. The method 2 is based on the microwave circular polarization. And then I will present also in the following slides 2 new methods that I've implemented in my laboratory. Both are based, method 3 and method 4 are based on lock-in detection, where essentially use a lock-in amplifier to demodulate the PL signal by using and modulating the magnetic field amplitude. And this can be done, this technique works both on resonance, like with using a resonance signal from an ODMR spectrum, or off resonance. Therefore, let's say in this method doesn't require any microwave radiation. And so therefore we don't need even a microstrip line for exciting magnetic resonance transition in MV center. Okay, let's start with the first method, DC bias method. This method is essentially a subtractive method. It's based on application of very strong bias field, much larger than the sample magnetic field, in such way that the total magnetic field is as the same sign of the bias field. Therefore, if you subtract the bias field to the total magnetic field, you obtain the correct sign for the sample magnetic field. So the mechanism for the bias field is shown in this slide, where the effect of the bias field is, of course, to shift the energy levels by Zeeman term in the spin Hamiltonian. And if we focus on one of the 2 transitions, let's say the 0 to +1 transition, and then we applied the sample magnetic field, so the field of the sample that you want to study, this has the effect to add or subtract to the bias field. And therefore, this effectively shifts the energy levels to higher or lower values. And so this means that the resonance transition are shift. Therefore, the transition from 0 to +1 will shift to higher frequency for the positive sample field, or to negative or to lower frequency for the negative sample field. And so these are actually the results that you get if you measure the ODMR spectrum. You see that your resonance line will shift to higher or low frequency depending on this on the polarity of the sample. And then we can exploit this phenomenon, this effect, in order to detect real time the magnetic field polarity if we simply monitor the PL signal at a fixed microwave frequency. Usually this microwave frequency is the one corresponding to the slope of the at the slope of the where there is the maximum sensitivity of the resonance line. And therefore, the effect of the external field of the sample field will be to increase or decrease the photoluminescence signal, which can be correlated to the sign of the sample magnetic field. And this method has actually been employed to study a variety of materials in condensed matter physics, like, for instance, permalloy, where similarly to the early days experiment of Michael Faraday to visualize the magnetic field around a permanent magnet by using powder of iron, they have imaged the magnetic field around the permalloys with different shapes, like a square or triangle. This has also been used to image magnetic bits in hard disk devices with a high resolution, and also to study the magnetic domains in 2-dimensional magnets. In this case, for instance, in the case of chromium iodide and chromium bromide, the magnetization has been found to vanish for a even number of layers and to have a net value in case of odd number of layers. Therefore, showing that this is to be a useful method to detect the magnetization which is dependent on the number of layers. Another nice experiment reported here is the possibility to use this method to detect a fully characterized magnetic vortex in a square ferromagnet, where we can fully characterize the vortex by its chirality and the polarity. So the chirality is if the spin are turning clockwise or anti-counterclockwise, and the polarity will tell you if the spins are pointing upwards or downwards. And last example reported in literature is the possibility to use this method to detect spin cycloid in a multiferroic material like bismuth ferrite. And this spin cycloid is as long as 70 nanometers and has been successfully detected as shown in this image here. And interesting, the authors of this work also show how the polarity of the spin cycloid can be controlled by electric field exploiting the magnetoelectric effect on bismuth ferrite. So let's move now on to the second method. So the second method is based on microwave circular polarization. So the downside of the method one, based on the bias field, is that we need a very strong bias field, usually of the order of few millitesla. And also we need a pretty bulky device where we need Helmholtz coils, which are bulky, and they must provide this homogeneous field around the magnetic field, around the crystal. But so we can avoid the use of bias field by using microwave circular polarization, exploiting the fact that the circularly polarized microwaves can excite independently the transition from the 0 to +1 or 0 to -1 energy levels. And this effect can be exploited, these selection rules can be exploited for detection of magnetic field polarity in a very elegant way. In fact, if you measure ODMR spectra for a fixed polarization, then you will see that if a magnetic field is pointing upwards, you will see, let's say, the resonance line appearing at high frequency. And if it's pointing downwards, you will see a resonance line appearing at low frequency. And so this provides a very easy way to detect the magnetic field polarity. And but in order to implement this method, then you need to be you have to design a rather sophisticated microstrip line because in order to have a circular polarization, you have to make sure that we have two input ports where the two microwave signals are shifted by 90 degrees with the same and carrying the same amplitude. And so you need to have a way to design carefully this strip line and make sure that they don't interfere either with the sample or with the external factors like external electric field and noise. And so these are very sensitive and delicate devices. And here are some examples of how they fabricated devices, the microstrip line with different geometries, like orthogonal two strip line or crossing strip lines and orthogonal four strip lines. In all these cases, they successfully show that it's possible to detect one or the other resonance line depending on the magnetic field direction. However, this method, as far as I know, has not yet been implemented on a real sample to study, for instance, spin texture in nanomagnets. So now, before moving to the third method and the fourth method, which are based on lock-in detection, I would like briefly to recall how a lock-in amplifier works, the working principle. So essentially, the lock-in amplifier works as a very narrow bandwidth low noise amplifier, and is based on lock-in reference signal, which carries an oscillating signal with a certain frequency phase, and which put into oscillation the signal they want to measure. For instance, in our case, is the photoluminescence from the MV center. And these two signals are phase-locked with respect to a internal reference signal of the lock-in amplifier. Now, the core of the lock-in amplifier is the mixer, which multiplies the two signals, F1, F2, giving a signal which is composed of two terms. One is given by the difference between the frequencies and the phases, and one is given by the sum of the frequency and the phases. And because in our ODMR experiment, the reference signal carry the same frequency, oscillate the same frequency, here we can, this term, the difference of the frequencies goes to 0. And therefore, we are left with the two terms. One is simply completely independent on time, therefore is a DC signal. And the second one instead oscillated double the frequency of the signal, of the reference signal. Therefore, we can, by using a low-pass filter, we can disregard the high-frequency signal, and we are left only with the DC signal, so which is easy to detect, and then and it is free from the frequency-dependent noise. So this method is usually applied for conventional electron spin resonance measurements, where you detect the microwave absorption by as a function of the external magnetic field, and then when you are in Renson's condition, you see absorption from the sample, and you can see that if you modulate now a portion of the spectrum with a high frequency but small amplitude magnetic field, then the lock-in amplifier provides a signal which is amplitude is proportional to the slope of the absorption peak. Therefore, you obtain directly the first derivative signal. And this is the experimental setup which I have employed in order to implement the lock-in detection methods. So briefly, I have used a green laser that is reflected by the correct mirror as a focus through an objective onto the diamond crystal. In this case, it is a microcrystal with a high concentration of 2-3 parts per million MV center. And the fluorescence emitted by the MV center is collected by the objective and sent back to the photodiode, then which gives the signal is input into the lock-in amplifier, which the lock-in amplifier then provides an output signal to the modulating signal to the coil that is placed in proximity of the crystal. Then we also need, of course, the microwave module in order to excite microwave transitions in MV centers, which are placed on top of a microstrip line. And then we have also a DC bias field, which mimic the sample magnetic field. So the protocol employed for the measurement is that the laser is being kept constant during the time. The microwave frequency is swept in order to reach the resonance condition. And then we have this magnetic field produced by the coil and the output of the lock-in amplifier that oscillate at a given frequency. And then the signal, this shows that what you expect to observe is a first derivative signal of the PL fluorescence from the MV center. And this is an example of what we observe, actually an experimental spectrum recorded, which showed the first derivative of the 8 MV center in, let's say, or the 4 MV centers in diamond. So this slide I showed a comparison between a conventional ODMR signal, where you can see the 8 dips that only looks like show a decrease in the photoluminescence, and the lock-in detected signal, where you see a signal at the same frequency of the conventional ODMR spectrum, but they have a first derivative line shape. Now, what is new in here is that we can note that if you look carefully at this first derivative signal, you can see that the one on the left-hand side corresponding to the 0 to -1 transition, and the one on the right-hand side corresponding to 0 + 1 transitions have opposite symmetries. So here on the left, they go from first down in signal and then up. Instead, on the other side, they go first up and then down. And this effect actually can be also observed if you sequentially measure 2 ODMR spectra by inverting the polarity of a magnet, of an external magnetic field. In fact, you can see that the 2 spectra mirror completely each other. whatever signal was positive for a given polarity, now is negative for the opposite polarity. In addition, you can also see that the background is actually not only shift with due to the different polarity, but also change sign from positive becomes negative. And so these two effects, the on-resonance effect and the off-resonance effect, so the signal from the background, can be exploited somehow to detect the magnetic field polarity. And this is what I'm going to show you in next. So I would like to point out a very important difference that has been probably overlooked in the past, that when you applied the magnetic field amplitude modulation, you get, that's the case I report in here, you get first derivative signals. But what usually people do in ODMR with the MV center is to modulate the microwave frequency. But if you modulate the microwave frequency, what you get always like first derivative signals, but all have the same symmetry. So there's no inversion between the transition between 0 + 1 and 0 - 1. And so this actually makes this the key point to that can be exploited for detection of magnetic field polarity. So based on magnetic field amplitude modulation and not on microwave frequency modulation. So the way to understand why we have this switch of symmetry this can be understood by looking at the energy level diagrams. So if you see that when we apply the magnetic field, there is the Zeeman splitting of the spin triplet in the ground state of the MV center. And then if you apply the modulating field, this effectively is a change in modulating the energy level from high frequency, so leading the transition from 0 to -1, from high frequency to low frequency. So modulating the microwave resonance line from high frequency to low frequency. Instead, the transition from 0 to +1 is modulated from low frequency to high frequency. And therefore, this means that effectively the PL spectra, ODMR spectra, are modulated from one transition from low frequency to high frequency, and the other transition from high frequency to low frequency. Therefore, the phases of these signals, of the PL signals, are opposite for both transitions, thus leading to opposite symmetry. Now, if we switch the polarity of the magnet, what happens is that the energy levels now are swapped. Therefore, the signal that was first scanned from low frequency to high frequency now is reversed, and so their phases. And therefore this leads to a spectrum which now mirror completely the one recorded with the opposite polarity. So these are the experimental spectra that have been recorded by changing the polarity of the external applied magnetic field. You can see that the two spectra completely mirror each other, and we can exploit this effect to detect in real time the magnetic field polarity. In fact, we just have to simply monitor the lock-in signal at a fixed microwave frequency. And then if you apply like a magnetic field polarity which switching simultaneously alternatively from positive to negative, like in a square wave signal, then we obtain a lock-in signal that resemble that change according to the switching magnetic field polarity. And so this open, therefore, the possibility to detect, for instance, digital information in magnetic hard disk based on, let's say, molecular magnets or spin texture, new spin textures in topological magnets, for instance. So the fourth method I'm going to present is based on all-optical method. And all-optical detection of a magnetic field polarity is based on a phenomenon called spin mixing effect. So whenever, in this case, no microwaves are involved in our experiment, but the fluorescence signal is measured as a function of magnetic field. You can see that the signal decrease because of so-called spin mixing effect. So which means that the MS states of the ground state of the MV center are any longer a pure state. but they are mixed between each other. So every state has a component of the other one. And therefore, this leads to a decrease of photoluminescence, and also to the consequence on the ODMR spectrum. If you, it's very important because the ODMR signal is completely quenched, and this is because this effect, the spin mixing effect, leads to a spin independent signal. So it's important to note that this effect, spin mixing effect, can be observed only when the magnetic field has an off-axis component with respect to the MV center. So it can be eventually transversal to the MV center direction. And the important thing is to note that although the ODMR signal is completely quenched and therefore becomes useless to detect any signal, the fluorescence signal is only quenched by about 15% for magnetic field up to 35 or 40 millitesla. And this gives the possibility to measure, lower the distance between the sample and the probe, for instance, in a scanning tip platform, where thus enabling much higher resolution of the magnetic field from a surface. For instance, in this case, by applying this all-optical method, the tip of the AFM microscope could be, with a nanopillar attached to it, could be brought close to the sample at a distance of about 30 nanometer. And I'd just like to note that at this distance, the magnetic field from the sample could be of the order of a few millitesla or tens of millitesla, which completely quench the ODMR signal, or also like separating the resonance frequency so much to be outside of the resonator bandwidth, therefore making ODMR impossible. So the experimental setup that I've used for lock-in detection of in the method 4 is essentially the same as for the previous method, that with the only difference that we don't use the micro module and for the microstrip line. And the protocol consists of applying a constant laser signal. Then we use a modulating field at high frequency, like 1 kilohertz, but small amplitude. And on top of this, there is a alternating magnetic field, which polarity switch from positive to negative. And what you expect to observe is that the PL signal should also be modulated at with the same shape of the external field. And this is actually what we experimentally observe. That's these are experimental data. They show how the PL signal shifts from positive to negative by alternating the magnetic field polarity. So the mechanism underlying this phenomenon can be explained by looking at the decrease of photoluminescence in the presence of an applied magnetic field. In this case, the oscillating field modulation amplitude is actually modulating the PL signal from high value to low value. And this provides a PL signal for oscillating the same frequency and phase of the modulating field with a phase difference, zero phase difference, providing a positive PL signal, which remember from the lock-in theory, this is proportional to the cosine of the phase difference. And being the phase difference 0, then we have a positive PL signal. On the other hand, if we switch the magnetic field polarity, then what happens is that the PL signal always keep decreasing with the magnetic field, despite of independent from the polarity. But now the magnetic field, oscillating field, is modulating the PL signal from low value to high value, and therefore with the opposite phase compared to the previous case. Therefore now delta phi is 180 degrees. And therefore, from the lock-in amplification, amplifier, we get a minus PL signal, so the cosine of 180 degrees. So this mechanism for explain why you observe positive and negative PL signal for opposite polarity. So a key point to make these methods 3 and 4 advantages compared to the bias field method, it's important to monitor what is the smallest. The question is, what is the smallest magnetic field that you can use for your modulation amplitude in order to still be able to detect a magnetic field polarity from your sample. And therefore, a study has been done by recording the method 3 and method 4, the PL, or so the on-resonance, off-resonance signal by using an alternating magnetic field and by decreasing the modulation amplitude of the oscillating field. And we found out that we can still detect distinguish the polarities between the two states for a field down to about a few microtesla. And then we can plot the response of the signal of resonance and resonance as a function of the magnetic field amplitude, and found out that we can achieve a larger response for the on-resonance with respect to off-resonance signal at the largest magnetic field amplitude. And then we also obtained the sensitivity of these two methods by analyzing statistical analysis of the noise level, where we achieve microtesla sensitivity in both cases, which are completely compatible with the sensitivity usually reported with ODMR spectroscopy with MV center. Okay, in conclusion, this is my last slide. I conclude with a summary and a comparison between the different methods. So I have presented the DC bias field method, which provides a very easy implementation. This method has been routinely implemented in laboratories, but the cons are that it requires a relatively large magnetic field, which can interfere with the virgin magnetization state of the material that you want to study. And on the other hand, it needs a bulky setup because of these Helmholtz coils that have to provide this homogeneous field at the position sample location. The microwave circular polarization method, on the other hand, doesn't require any external magnetic field, therefore it's much more compact setup. However, the downside is that it requires a very high skills to design these microwave strip lines with a high degree of control of the phases between them, the polarization of these microwaves, and therefore the phase between the two microwave ports. And in addition, I think as far as I know, there are no real application in real samples so far, except for this method and not yet, let's say, implemented on real samples. And finally, I presented the method 3 and method 4. These are new methods that I implemented in my laboratory, and they consist both on lock-in detection, one based on detecting based on magnetic field modulation of on-resonance signal and off-resonance signal for method 4. So the advantage of the magnetic field on-resonance method is that we need a very small magnetic field within microtesla of the order of microtesla, instead of for the DC bias field we need usually millitesla. Provides also a compact design and relatively high sensitivity, and the cons is that it still requires microwaves. And microwaves can also be an issue with some samples. For instance, they can provide heat up the sample, or can also microwaves radiation can interfere with the magnetic properties of the sample that you want to study itself. And instead, the microwave-free method, of course, doesn't require microwaves, so there's an advantage. Also enable a much smaller distance between the sample and the probe, therefore enhancing the spatial resolution. The cons are that it provides a slightly lower sensitivity compared to method 3, so the resonance method. And one question is that can be further investigated regarding these methods is what is the detection speed? And for instance, how fast we can detect the switching of magnetic field polarity. So this will be important to study spin dynamics and, for instance, the switching field of the magnetization in samples. And finally, I would like to acknowledge the research funding that supported these activities. So the University of Milano-Bicocca and the BQT, the ODMR lab in the Department of Material Science, the Bicocca Quantum Technologies, and the European for funding like the National Quantum Science and Technology Institute. And finally, of course, thank you for your attention.
Fabrizio, thank you very much for beautiful talk. It seems that there is some well-established area, but then there are still new advancements are possible. So it is exciting to see as you bring this phase-sensitive look in to advance the magnetic field measurements. Do you see any ways that sensitivity can be improved to nanotesla level?
Well, actually, well, this can be I mean, this can be employed, for instance, by using different like these experiments have been done using very high concentration crystals with high concentration NV centers. And therefore, it's possible that the spin coherence time could be lower, and this lower the sensitivity. So that's my guess. But the method itself can be applied from a crystal with a single NV center to any concentration, I think. So that's there should be an issue. Therefore, can be tested on other crystal that can provide better sensitivity. And also, eventually, not only the nanotesla sensitivity, but also to bring this method down to nanoscale resolution. In fact, one of the things I would like to do is try to implement this method by using the scanning tip platform. So attaching a nanocrystal to a FTN tip, and to implement this method in this type of platform, rather than just using optical microscope.
Yeah, I have a quick kind of related question. So yeah, this is awesome talk. It's really, really enjoyable. And also like congrats, because I think these papers are like, they just came out, didn't they? Like I think one is maybe still in press.
Yes.
But what samples were these single crystal, or were these micron particles? I don't remember.
That was actually a microcrystal from yours, actually.
Microcrystals, okay.
Yes.
So the related question that I was trying to think about in these experiments is, you're implying that the particles must be fixed so that you have a known axis. To what degree could there be modifications as if the particles are in some sort of movement, or if you rotate the particles? How does that change how you might interpret the data that you're collecting?
Well, that's actually, as long as the main point is that you have to be able to detect, I mean, the orientation of the particle will change the magnetic field projection on your MV center. No?
Yeah,
so
exactly.
if you have an ensemble, then the magnetic field will split the resonance lines. And then what you have to do is actually just focus on one of the resonance line, and then monitor that resonance line by switching the magnetic field polarity. So in principle, I mean, if the magnetic field from the sample is very weak, like a micro Tesla, or below smaller than 1 millitesla, then probably that won't be even noticeable on your ODMR spectrum. But all you have to do is actually to see how even let's say very close to zero field, how the signal is reverting sign. So that's actually is not a key point that can jeopardize the applicability of the method. I think it's very general. It can be applied from a single crystal, having an ensemble MV center, low concentration, or even to a single MV center.
Yeah, because really interesting, I think, is that there are applications where having small particles that are actually in some sort of environment, where their location might not be fixed. It's an interesting
the location fixed, that could be an issue, because then if that will shift the resonance lines,
exactly, that's a bit of a challenge.
That could be eventually you have to just record the whole spectrum all the time. But of course, this will lower the detection speed.
So the other question that I'd noted down kind of in your conclusions for the last two methods that you had described, method 3 and 4. Do you have estimates on what the detection time is and maybe what the best case scenario is for being able to detect changes in spin? So you mentioned that might be like a drawback, but what is the scale that would you estimate?
Yes, I think that will depend on the. Usually, when you do a typical APR experiment, right? When you want to study spin dynamics, you don't use a lock-in detection. You just go straight for detection of magnetic field microwave radiation from the sample. So you skip the lock-in because you want to have, let's say, nanosecond resolution. And if the sample they want to study is on the time scale, that lock-in amplification is not the right way to do. It is based on what is known for APR. Now, we have to apply this, translated this to ODMR, and this could be even more complicated to understand. But overall, I think the time scale is fixed, is somehow constrained by the modulation field frequency that you can use, and also the throughput time of the lock-in detection itself to process the information and to have your signal. And this is something that we still don't know. We want to clarify and see what are the detection speed. So far, I could do the experiment only on, let's say, few hertz time scale, frequency scale. So that's, yes, I have no exact answer for this question, but it's something I want to explore.
Exactly. Yeah, cool. Thanks.
Please just unmute yourself and ask your questions if you have some.
Yeah, Fabrizio, yeah, great talk. I had a couple, like maybe technical questions and maybe I just missed. When you do your field modulation of the magnetic field, what is the amplitude of that modulation that you're using? Because typically, yes, like in typical EPR, your field modulation needs to be smaller than the line width, right? Or else you can distort your spectrum for things like that. So I was just curious, like, when you modulate your magnetic field, what the amplitude is and what frequency you were doing that at. Is it like 100 kilohertz? Do you run into issues with like the field being unstable due to heating or anything like that?
Yes, I show that the magnetic field, we have done the magnetic field. I don't know if you can still see can you still see my presentation?
Yeah.
Yes, yes.
Yeah, yeah.
But I cannot switch the slide. Can change the slide somehow. It's
maybe exit presentation mode, and maybe that'll help.
No, okay. Anyway, so what we have tested is that the modulation amplitude can be as small as from what we have tested was from about 30 microtesla to a few microtesla. So, and then actually how that convert, you should convert that in the frequency line width actually, and see how this translate into frequency in the frequency domain for the ODMR spectrum. So that's a right answer. I think it's a very good question. And so the way, I don't know exactly the maths to do that, but what empirically you can do is to monitor the line width of your ODMR spectrum for different modulation amplitudes. And the point is that when you see that the amplitude is getting larger for a given modulation amplitude, that means that your modulation amplitude match the line width of your resonance line. So that means we are over-modulating your signal. So in principle, you're right, you want to keep your modulation amplitude as small as possible to have a high resolution spectrum. But the question is, unlike ODMR, standard DPR, where you want to have a high resolution on your spectrum because you are interested in all the, let's say, all the frequencies, all the resonance frequencies, no, the upper fine interaction and so forth. in this case, if you just wanted to know the magnetic field polarity, then you just want to know the sign of your signal. And then it doesn't really matter if you are over-modulating or under-modulating your signal. Of course, you have to optimize in order to have a maximum difference between positive and negative sign.
And then like the frequency of the modulation, is it you're doing like so like to EPR, typically like 100 kilohertz modulation frequency at like maybe 1 Gauss amplitude or something like that. So you're doing you test like microtesla or 30 microtesla or so at like what frequency? I was just curious.
No, in this case, the frequency was kilohertz, 1 kilohertz.
Okay.
Few kilohertz, that's actually what is found typically in ODMR experiment, also modulating with using modulation frequency. Is a few kilohertz usually.
Yeah. So yeah, since it's such a small amplitude, you probably don't have any issues with like heating of the. Well, I guess you're using like an electromagnet or anything like and you're doing it that way, and you have the modulation coils as well. But yeah, so you don't have any issues with like heating of the magnet, which would cause some like delay in the stability of them, right? Because there's some inductive effect when you like it doesn't respond instantaneously. Yeah, but
yeah, exactly. But the thing is that you're right. I've used just the coil, and the heating effect was at some point it was impossible to let's say increase the frequency or the modulation amplitude at some point. So but yes, can be something that could be improved technically. But as far as I know, the ODMR experiment by using Lokina detection I used on the frequency range of few kilohertz. So I think that just match what I have observed as well. So I don't think I had limitations in this respect.
Cool. Yeah, thank you.
That's good question. Thanks.
Yeah.
Hi, Fabrizio. Thank you very much for a very nice presentation.
Thanks.
I have two questions. The first one is, if I understood you correct, in the polycrystalline samples, the effect of polarity disappears.
No, the polarity is due to the external field, nothing to do with.
But detection in polycrystalline sample will smear out the effect of polarity. Is it correct?
But polycrystalline sample, what do you mean? A sample to study? Are you talking about the diamond crystal or?
No, okay. Yeah. I mean, if you have random distribution of different NV centers, and when you are working with the ensemble of randomly distributed NV centers, you will not see the polarity effect.
Maybe you can have a resolution, depends on if you have a polycrystalline sample, you have a spatial resolution that can, you can select an area where you have like homogeneous single domain. In the case, I think
you mean by doing very small detection area, you can
exactly. Yes, of course.
Question?
Yes. Second.
Okay,
yes, please.
Thank you. And the second question is: have you ever tried something like fast passage in this?
No, I know this technique used usually for
very low modulation amplitude and additional fast scan of magnetic field.
Exactly. Yes. The scanner was very usually. I think in fast scanning use a very fast magnetic field that scan through a resonance line. Is that correct?
Yeah,
no, I haven't tried it.
The same fast passage you can do for microwave.
No, because I think I have a very slow microwave. Let's say microwave module. Therefore, that's very slow. It's like a constant over with respect to the modulation frequency. So it's not as fast scanning at all. No. that I couldn't implement, actually. I don't think that I have the setup for doing that.
Okay, thank you very much. Thank you again.
Thanks.
Okay, it looks like we have no more questions. It was a lot of questions to Fabrizio, which is always great thing for a lecturer, right? To have
yes,
variety of questions. Fabrizio, thank you so much for your great presentation. It's really very well structured. It was prior art. So even if it's not my field, I learned a lot from your presentation.
All right, thanks a lot. Thanks for this opportunity. And I thank everyone for participating and for your time. Thanks a lot.
And good luck with your future research. Now
Thanks.
to bring
Same to you.
your method to real world, right? To measure some real samples. So it will be.
Hope we can be in touch then. Can still in touch.
Yeah, let's stay in touch. Yeah, definitely.
For more samples, maybe. Thanks a lot.